All right, here we are with the second video in chapter 1, and here we're going to talk about math and its uses in science, particularly how we round and how we use significant figures. So to start off, the first thing you have to recognize is that in science or in chemistry, there are two kinds of numbers. There are exact numbers and inexact numbers. And you may wonder why we even deal with inexact numbers until you understand what they are. So exact numbers are ones that are defined. Like there's 1,000 grams in a kilogram, or there's 12 eggs in a dozen eggs. These can also be considered counting numbers, like counting the number of people in a class. So those are exact, and they have an infinite number of significant figures. Exact or inexact numbers, on the other hand, are numbers that have been measured. You can't count them, and you're using a measuring device, and how good your measuring device is determines how exact your number is or how good it is. So I have an example here of a measurement of an SD card, and we're going to look at the number of significant figures or the meaningful digits that you can get. That last digit in the measurement is your uncertain digit, and you achieve it by guessing. So if you use this top ruler, you can see the SD card's width is over 2 centimeters, and you get to guess where it is between those last two marks. So you say, well, it's 2.5 centimeters, but it's plus or minus 0.1 centimeters, plus or minus one of that last division you're guessing. And we get to guess because we're human beings who are considered intelligent beings, and therefore our guesses are worthwhile. Now, if we use the bottom ruler that had more divisions, so it's a better measuring device, now we can see that the SD card is over 2.4 centimeters, and in fact we could guess it at 2.45, and then that's going to be plus or minus that division you're guessing, which is the hundredths of a centimeter. So generally speaking, the better your measuring device, the more certain your measurement is. So we want to use the best that we can. Now, once we have good measurements and significant measurements, we need to look at how can we handle those in mathematical calculations. And the first thing we have to do then is to be able to identify what are significant figures. So if we look at this first example, any non-digit is significant. So 112.1 has 4 significant figures. If you've got zeros in there, it starts getting a little trickier, but if they're between non-zero digits, then they are significant. And so 305 has 3 significant figures, 50.08 has 4. If your zeros are to the left of the first non-zero digit, they are not significant, as can be seen in these two cases, because they're just placeholders. And one of the best ways to determine how many significant figures there are is to put your number into scientific notation. So that first number, 0.0023, would be 2.3 times 10 to the minus 3. Whatever the units are, and that 2.3 shows you there's only 2 significant figures. Another example is if the zeros are to the right of the last non-digit 0, they are significant. It says yes when we were measuring it was right on the line. So 1.200 has 4 significant figures. But if you have a number that doesn't have a decimal place, your question of how many significant figures you have is going to be very ambiguous. And so to avoid ambiguity, the best thing is to use scientific notation, as I discussed in the previous slide. So if you know from your measurement that 100 is really 1 times 10 to the minus 2, then that means you only have one significant figure. But if you know it was better than that, and you know it was really 1.0 times 10 to the 2, then that tells you you have two significant figures. So it's always best to go to scientific notation. All right, so there's an example here of just trying to figure out how many significant figures you have. And so in the first one, obviously there's no non-zero digits, and so there's 3 significant figures. In the next one, we have 4 because the 0 is between non-zero digits. In C, that the preceding zeros are placeholders, and so they don't count. So we only have 3 significant figures. But in D, it's in scientific notation, so we know that all 4 of those digits, the 3.000, are significant. When we look at E, we see 50 milliliters, no decimal point, so it's very ambiguous. If it had been written as 50 decimal place, and we would say it was 2 significant figures. Better yet, put it in scientific notation. And then, of course, that last one has 4 significant figures. So once we can figure out how many we have, now we can address a question of how we do the math. And so if you're doing addition or subtraction, the key is to line up your decimal places. In that first example, you have 50 past the decimal place, and those are significant, but it's being added to 0.231, so you have 3 places past the decimal point. And so when you line them up and add them, there is no significant amount to add to the 1, which is the last decimal place. And so you have to drop that decimal place in your answer. And so the answer, because that's dropped, becomes 102.73. In the subtraction example, the first number has 2 decimal places, and the second number, what you're subtracting, only has 1. And so you can only have 1 decimal place in your answer, but you do get to round up the number. And we're going to talk more about rounding rules. So in addition and subtraction, you conserve decimal places. But if you are looking at multiplication or division, now we want to keep track and conserve the number of significant figures we have. So in the first example, we have 2 significant figures multiplied by 4. So your answer can only have 2. And since it's 11.2154, you drop everything from the 2 on, so the answer becomes 11, which is 2 significant figures even without a decimal place because they are non-zero digits. In the second example, you're dividing 4 significant figures by 5. So your answer can have 4. And so that's going to be the 3782. And now we have to ask ourselves what we do with that 5. And there is a number beyond it, so it's greater than 5. So we're going to round up, which is shown here in the answer, 0.03783. So when we do multiplication or division, we conserve significant figures to the lowest amount of significant figures in the numbers involved in the problem. All right, so one last question about calculations, and that's if you have a measured number and an exact number. Well, exact numbers are considered to have an infinite number of significant figures, so the number of significant figures in the answer is determined by that measured number. So in this example, you have 3 pennies, so it's a counting number. So 3 has a unlimited number of significant figures. our mass of 2.5 grams has an uncertainty, and so when we multiply those, we have our least number of significant figures is in the 2.5, so our answer can only have two significant figures as well. All right, so then I told you we would talk about rounding, and one of the simplest rules for rounding is if that first number that you're going to drop is less than a 5, then you round down, and if it's equal to 5 or greater than 5, you round up. However, the rounding rules we are going to use are not quite that simple. If that first digit, which is just past the last significant figure, is less than 5, you drop it. But if it is greater than 5, you round up. But if it is 5, then you have to look at the other digits that are after the 5. And if there are other numbers past the 5, then you round up, as we did in that last example. But if the 5, if it just ends with 5 and yet your digit past the least significant digit is strictly a 5, then what you're going to do is you want to go for an even number. And so you round up if the preceding number is odd, and you round down or you drop it if it's an even number. So the other piece of advice I would say is if you are doing a set of calculations on a calculator, you keep track of your significant figures, but you never do your rounding until the end of the problem, because that calculator is doing rounding and truncating, and you can come up with rounding errors if you round off too early. All right, so the other thing about measurements we need to know is their accuracy and their precision. And these are terms that are kind of confused in the common vernacular, but accuracy is telling you how close you are to the true value, whereas precision tells you really how good your measuring methodology is. And if all of your answers are really close together, then you have a very precise measurement. And we have an example here to help you sort of visualize this. If someone threw 4 pieces of paper into a trash can and got them all in there, then that's good accuracy and good precision. If they threw them all and they ended all up on the left side but none in the basket, it's good precision but poor accuracy. And if they're just spread out all over the place, it's poor accuracy and poor precision. Another example that's often given to understand precision versus accuracy is shooting arrows at a target. If all of your arrows end up in the target, then you have good precision and good accuracy. If all, say, 3 arrows end up to the right side of the target, then you have good precision but poor accuracy. And if they're just all over the place, then you have poor accuracy and poor precision both. All right, so now we have an example. You had 3 students who had to find the mass of an aspirin tablet. We know the true mass is 0.70 grams. And here's the data graphed, so it's very easy to see. And I'll give you a second to think about what it is. Student A's are very close together, but they're not close to the known value. Student B's are pretty much all over the place, and they're not centered on the true value. But student C, all of their values are very close and right on top of the true value. So what you have is student A's results were precise but not accurate. Student B's were neither precise nor accurate, and student C, their results were both precise and accurate. All right, that's the end of our second video, and we will have 2 more to go.